That is true, but making websites, are is a lot easier than before. Yep. Well, WordPress is just a publishing, engine, right? But the actual content can also be generated for the most part. Um, yep. And you can even ask ChatGPT. I'll bet you can ask your ChatGPT, how can I improve the visibility of my web page and get more clicks? It will give you the idea. Or you can even say, okay, give me the HTML code that I can copy and paste. It can do it already. All right. Well, now that most people are showing up, I'm going to get started with today's lecture. We are now moving on to kind of like I would say the middle part of the semester, which is actually about right. I think this is about week 5, right? So on Thursday, we're going to go over the practice exam, or what you would think consider as a practice exam. It is in the announcement already. So if you have not read it yet, you might want to read it. I believe there's an attachment here. So this attachment is the actual first exam from last semester. So, if you have not opened it, I strongly encourage you to open it so that you can at least get an idea of what it looks like last semester. Um, but we will talk about it on Thursday. But it is more helpful, much more helpful, if you spend some time to study and try to answer the questions before the class, okay, so that you can bring your questions to the class. Like, I really cannot figure out how this connects to that or how to answer this particular part of the question. So it'll be a more productive use of our time on Thursday. So this is available. All right. So what we're going to do is now we're transitioning to the von Neumann architecture and memory. Basically, we are going to get into the processor itself. What we have been doing in this class is we are building a computer from the ground up. We started off with two P transistors and two N transistors, making a NAND gate. And then we talked about how to use NAND gates to create the regular OR gate, the regular AND gate, and the regular NOT gate. So then we have the three logic gates corresponding to the three the Boolean operations that we have learned in CISP 300 as well as CISP 360. And then we shift gear a little bit to talk about base conversion, because base 10 does not lend itself to logic gates. Okay, but then we talk about general base conversion. We have a general scheme. We can convert to any base that we want to. But of all the bases, base 2 is particularly of interest to us because in base 2, the two digits that are available are 0 and 1, which is great because now your logic gates has true and false. So now we can look at true as 1, we can look at false as a 0. So if we can convert all the operations that we need to perform into logic gate operations, and or not, then we can implement everything in silicon, which is kind of the whole purpose of, part of the purpose of this class. So after that, we also shifted gear to talk about addition and subtraction. So we started off with base 10 addition and base 10 subtraction, multi-digit. We look at the structure of addition as well as subtraction. What is the carry? How do we compute the carry? What is a single digit sum? What is a single digit difference? And so on. So none of that is new. Okay, if you know how to carry out a base 10 multi-digit subtraction or addition, you already intrinsically understand all that stuff already. All I did was to formalize. Okay, I introduced the symbols to formalize everything. I introduced the functions, the R function, the C function, the B function, and then I name all those rows of digits in very strange ways. Okay, but all that really was a formalization of something that you already know. So when you look at the R function, the C function, and the B function, there's only one place or a few places where they refer to the base of the number. Okay, so in base 10, you see the actual number 10. In base 7, you would use 7 instead. So converting everything to work in base 2 is easy. We just have to convert all the 10s into 2s, and now they work in base 2. But the one thing that we found out about base 2 is the R function is just exclusive OR. The C function is just conjunction, and then the B function is a little bit awkward, because the B of xy is the negation of x and y. But nonetheless, it can still be done using logic gates. So that was kind of the journey to do computation. And then once we talked about addition and subtraction, then we kind of talked about representation again, because we have always been only talking about unsigned representation. So we shift the gear again to talk about signed representation. How do we represent negative values when all you have are zeros and ones? You do not have a negation symbol at the beginning of a number. All you have are zeros and ones. So as it turns out, the way that we represent negative numbers is related to um, congruent modulo some power of 2, kind of mathematics, which also led to 2's complement as a method in order to perform arithmetic negation. So that's kind of a big, long journey, okay? And then we talked about comparison, which is based on binary subtraction. So we looked at the borrow flag after a subtraction, and then we also looked at the sign flag of the difference, which is okay, but not sufficient. And then we also have to look at the overflow flag. And then between the sign and the overflow flag, we combine those two into the L flag, which will tell us whether x is less than y or not. Okay, so but that's all that the processor knows how to do intrinsically. It's really just addition, subtraction, and comparison. Okay, everything else is based on these three operations. Okay, so that with that all done, okay, now we are shifting gear to look at to take a step out. Okay, so we have the mechanism to perform computation, addition and subtraction, and also comparison. Those are the only kind of computation you need a computer to do. But then we need a lot of peripheral logic or peripheral devices in order for programs to work. Okay, just being able to add is not enough. In other words, where do we get the values that we're adding? And once we are done adding, where do we put the sum? Okay, we need places to store all of that stuff. So that's why we are shifting into the von Neumann architecture. So before we get into the von Neumann architecture discussion, I am going to show you a picture of how computers used to be before the von Neumann architecture. So we are looking at computers with um, hard wired logic, and these are usually called wire wrapping. Okay, so wire wrapping. Um, and then we're going to look at images. There we go. This is a pretty good. And this is not too long ago. It is a computer. Okay, on one side it looks kind of neat. All the chips, being well organized. And then on the opposite side, let me see, right there. This is how it is organized. Now, this is not even the worst, okay? Because it already has a processor, so we are only interconnecting chips, okay? In the even good in the even older days, okay, there's no such thing as a processor. So if you want a computer to do a specific kind of programming, you have to hand wire the adder, the subtractor, and then the registers and whatever. They're all connected by wires. This is by comparison a simple computer. Yes. Hmm? They don't have zip ties. Zip ties won't help. You just have more things to get rid of when you need to rewire a computer. Well, if you think that one was bad, let's take a look at yet another picture. And there we go. Okay, zoomed in. Yes. Now this one does have your cables, that are kind of bundled together and so on. This is what it takes to quote unquote reprogram a computer. Okay, everything is wired. Okay, terminal to terminal wiring. Okay, there's no such thing as over-the-air updating of an operating system. Okay, an update of quote unquote your computer is going to take at least days, if not weeks. And then you have to spend another month to debug it. Yes, but then the good thing is, it's kind of difficult to hack a computer because you really need to have physical access to the computer to hack anything. And the hacker better be able to do the job really quick because you only get a few hours before the next day, and then people come back and go like, "Hey, what are you doing to the computer?" So this is before von Neumann. Okay, this is before von Neumann's invention. It is because everything that needs to be done, the ALU, the arithmetic and logic unit, the adders, the subtractors, the comparators, they are all hardwired to get one particular thing done. Okay, so a computer can only get one thing done. You cannot reprogram it. So now we move on to this person, John von Neumann. So here's the guy. And Wikipedia has a really good page on uh, John Vonneman, and he is famous for a few things. Okay, quite a few things. He is. I think he is responsible to the construction of the hydrogen bomb, not the nuclear bomb, but the hydrogen bomb. So the fusion bomb. That's one of his contribution, which also, most people believe that that is also why he did not live very long, because they thought that he died of cancer because of the exposure to radiation. Um, so you would think that, okay, fine, he's just a genius, okay? Well, he's not just a genius. Okay, let me zoom out again. Eh, He is, so let's take a quick look at what he is good at. Uh, where is it? Why is the font so big? Now it's more, now it's more like it. Okay, I'm just looking at the introduction. It usually is at the beginning. There we go. All right, so he is a genius in mathematics, physics, economics, computing, and statistics. Now there are people who are well versed in multiple areas, but they're not particularly good in each one. He is one of the few exceptions. If you ask in his era who's the best person in mathematics, in physics, in economics, in computing, and statistics, they will all name him. So that's a kind of super genius that you're talking about, okay? Not just one thing, okay? But in just about everything. Okay, so you're free to read this whole page, to kind of know more about this particular person, who actually made a very significant contribution to computer science. Because without him, computers today would still be probably wire wrapped. Okay, with all those horrendous amount of wires, there won't be any handheld computers. There won't be any laptop computers. There probably won't be any desktop computers either. Okay, so he actually made a really big contribution. That one contribution that he made was, it would sound simple to us because we're used to that concept already. He says, well, in addition to using memory, the computer's memory, to store the information to be processed and also to store the result after processing, let's also use that memory to remember instructions. Okay, in other words, what the computer is supposed to do, let's store that into the memory of the computer along with the data. Because to us, it's like, oh, that's really natural. I mean, what else is there to be done? Well, we already saw, okay, the so-called instructions before his time were not actual instructions that is stored in RAM. They were in the form of wires, hard wiring from one component to another component. He is the first person that says, well, why don't we actually store those instructions that tells the computer what it is supposed to do also in the same memory that is used to store the data to be processed. That was his contribution. It doesn't sound like a lot, okay? But without that contribution, we wouldn't have the computers that we have today. Just about every computer today is a von Neumann architecture. Some of the other ones are also called the Hartford architecture, which is a modification on the von Neumann architecture. Yes, does he what? Alan Turing was never, never really imagined this kind of computing. So Alan Turing's computers were, he was much more focused on the mathematical modeling side of computing equipment. And almost every single one of you will have to take an upper division class called automata theory or the theory of computation. So that is Alan Turing's contribution. So it's a different contribution. I believe John von Neumann's architecture is a much more pragmatic contribution as opposed to Alan Turing's contribution, which is a much more on the theoretical side. All right. Okay. So now the next question is, how does a computer remember something? Okay, because now we have to get into memory. How do we store anything in a computer? So we're going to take a look at a very simple device, and let me get my tablet up and running. And all of this is in the notes already, obviously. So if you had a chance to read ahead of the class, I think that would be actually very handy. But if you don't, we'll talk about it now. All right. So what we'll do is we're going to take a look at a kind of special kind of circuit. Okay. So the circuit only has two NAND gates. Okay, so we have two NAND gates here, and I'll name the NAND gates. Okay, we'll call this N1 and we'll call this N2, just so that I can reference, which one is which one. Okay, each one has two inputs, and then we have an input pin over here. I'll call this input pin X, and I'll call this input pin Y. They are not related to the X and the Y of addition or subtraction. I'm just calling these input pins X and Y. And then on the output side, we have two of those. One is called Q, and the other one is called NQ, which is basically just the negation of Q, but it's not exactly just the negation of Q, as we will see a little bit later. That's the output, okay? The output of the NAND gates go to the output pins, and then the input pins connect to one of the input of each NAND gate. So now the interesting part, and this we have not seen with the other circuits, is there's a kind of cross loop thing going on here. Okay, that is a SR latch. Okay, so the name of this circuit is called an SR latch. SR latch. And it is the simplest device that can quote unquote remember something. Okay. Well, we look at this circuit here and go like, well, that looks like a loop, okay? But it's not even a well-formed loop because one thing goes to the input of the opposite side, okay? So how does it work? We're gonna play out a few scenarios, okay? So we're gonna play out a few scenarios here, and I will add a new layer so that I can hide and display different layers if I need to. So let me see right here, and we're gonna add a new layer. And layer 2 is the one being used right now. Okay. Now, how do I know which one is being in use? Hmm. Yeah. So I think I want layer 2 to be on top. Okay. All right. So what we'll do is we're gonna take a look at kind of look at this, from the perspective of a truth table. So we look at x and y, and we try to evaluate what happens when they are both zeros. Okay, and then we look at the output q and then q. So how do we analyze this circuit? Well, it's not a so I would try to do it in a very kind of casual way, and then we'll do it in a much more formal way. So we'll do it in a very casual way first. So the casual way of looking at this is X goes straight into one of the input pins of N1, and since N1 is a NAND gate, so that means the output has to be a 1. Very good. So that means Q is guaranteed to have a value of 1, and then NQ is guaranteed to have an output of 1 as well, because Y is a 0 and Y goes straight into one of the input pins of the NAND gate, in this case N2. Now, if you have this question in your mind of, why do we know Q is a 1 and NQ is also a 1, then you need to go back to the truth table of NAND, which I believe we talked about in the first week, not necessarily the first class, but maybe the second class of this entire semester. Okay, but I'm not going to go back and talk about that. All right, so that seems to be an easy one. So the next one, we'll take a look at what if we are to change y from a 0 to 1? So this is a sequence, okay? So we're looking at a sequence where x, y were 0 zeros before, and now I switch y from a 0 to a 1. So now it gets a little bit complicated because we can look at y, okay? This is y here. It was a 0, it now turns into a 1. This was a 1 already because it is connected to the output of N1. The output of N1 is still a 1, okay? So now we have 1, 1 here. That means the output is going to be a 0, okay? Hmm, okay. Q is still going to be a 1, but NQ is going to be a 0. Now we say, what if we are to change X also from a 0 to a 1? What is going to happen to this whole circuit? So now it is difficult to track because if you try to track everything in your head, this is difficult because we have to remember that N2 was outputting a 0, N1 was outputting a 1. So when Y is a 1, this is a 1, N2 continues to output a 0. But what about X? X was a 0, okay? And now it turns into also a 1. So from but the thing is the output of N2 is now a 0. Okay, I might have misspoken a little bit earlier, but N2 has an output of 0. So that 0 goes into one of the inputs of N1, which means N1 has had two inputs, both being zeros, and that's why output 1. Now that X turns from a 0 to a 1, it still has the second input being a 0, so it continues to output a 1. So let me just put a 1 over here, and that becomes a steady state. Okay, well, okay. All of these are steady states, which means it's not changing anymore. So that's one exercise, okay? And I will basically encourage you to go through another sequence, okay? So we look at another sequence here. So we have X, Y, Q, and NQ over here. The other sequence also starts with X, Y both being zeros, and Q and NQ are both ones. However, this time, instead of switching Y from a 0 to a 1, we switch X from a 0 to a 1, while Y maintains to be a 0. You go like, well, the circuit is kind of symmetric, so that means Q becomes a 0 and NQ becomes a 1. You would have been right. And then we switch both xy, or which y in this case, also from a 0 to a 1, and you will find that the output is like this. This is why we call this a latch, okay? Because you can see that after we set the xy up in a certain way, one is a 1, the other one is a 0, and then we transition both to be ones, then it maintains the state, and it maintains the state. So this is the quote unquote effect of being able to remember something. Now, it doesn't feel like it is significant, okay? But it is the basis of almost everything that needs to keep track of something over time. Yes. So basically, anytime you switch from any state into both inputs being 1 and 1, it maintains whatever state that the whole device was in. So when you look at 1 1, it basically means, oh, just maintain the state. Do not make any further changes. I'll be, yep, say that one more time. hmm Um, if one pin is a one input pins, okay, if one of the input pin is a 0, the other one is a 1, then it will change the state. But when both input pins are ones, it quote unquote maintains the state. If they're both zeros, we know that both outputs would be ones. So I think your question is, what if we are to transition from 0 0 to 1 1? What would happen in that case? So let me think, okay? Because that one requires what we call an analysis of propagational delay, okay? So, but are we okay with this rather informal or rather casual analysis of the circuit? We good? Yes, go ahead. How do we compute the Q and the NQ? Do you have any particular role that you want me to explain? So I described it verbally, which was very difficult to track, and that was kind of my point. Okay, it's difficult to track. So instead of answering your question right now directly, I will answer that question with a very formal method so that we can actually have a mechanism to keep track of the propagation of changes. Okay, but that was a very good question. Okay, that was kind of the whole point. Is okay, I'll give you a very casual verbal explanation. Some of you are nodding your heads, thinking, okay, I can track that. But most people probably feel a little bit difficult, to listen to all that stuff and track. Okay, so what is the output of this thing and what is the input to that thing? It's difficult to track. Okay, so that was kind of my point. Okay, because I need to talk about why it is important to have a much more formal way of keeping track of these changes. Yep. Um, yes. So Q and NQ together is quote unquote the state of the SR latch. So sometimes you want them to change, and sometimes you want to maintain that. Very good. All right. So are we good with this picture so far? Okay. All right. Yep. Mhm. Well, because we are using transistor, we're using MOSFETs, which are field effect transistors. They have very, very little current going on. The current is only used when you are switching the state of your transistor. Once the transistor is in a certain state, the actual amount of current being consumed is very, very low. So there are not a significant amount of current going through the wires, just a tiny amount. Okay, so we're going to take a step, into the actual transistor for the time being. So we look at the transistor, okay, it looks like this, and depending on whether it's an N type or not an N type, there's a bubble either here or not here, okay? So you can see how the gate, okay, let me just name the parts here. So this is the gate, and let's say this is a N type, so the arrow goes this way, this is the source, and this is the drain. But you can see that there's no actual connection, at least in the schematic, between the gate and the source or the drain. Okay, and that's kind of the whole purpose of a MOSFET. The MO part is metal oxide, and the S, I believe, is a separator or insulator. Okay, So there's an insulator between the gate, which is this little plate here, and the rest of the transistor. It forms what we think, what we call a capacitor. Okay, so there's a capacitor basically right here. This is a little capacitor right here, and every time you want to change the state of the transistor itself, like if the gate goes from 0 to a 1, it takes a little bit of time because every wire carries a little bit of resistance. It also carries a little bit of inductance. So that means, the change of the voltage at the gate is not instantaneous. It needs time to build it up. That's all we need to know. Okay, so this is not a physics class, so we're not going to talk about the actual physics behind the whole thing. But all I'm going to do is to say, as soon as you make a change here, it will take a little bit of time before the transistor, responds to the change. Is that concept okay? All right. So every transistor has a intrinsic delay from the time you change the gate to the time when the device is either turned on or turned off. Okay. So when you have four of these things, okay, I hope you still remember the four transistors. Okay. So this is a simplification of a NAND gate. Okay. So when there are four of these things, okay, each one of these transistor take a little bit of time to update its own state. So that's the time that we call a propagational delay. So from here on, you can remember that term. It's called a propagational delay. Propagational delay, and that is basically the time when the input pin change between when the input pin changes to the time that the device responds with the correct answer. Is that okay? So every gate has a propagational delay. Are we okay with that concept? Yeah, it is usually measured in nanoseconds, if not less. So it's a very, very tiny amount of time, but nonetheless, there is an amount of time. Yes. The propagational delay is the time between when the input pins change to the time when the output is correct. So to complete this circuit, okay, there's one input pin here. Oops, I just made a mistake here. Uh, Forget that part. Uh, Switch back to the pin like that. Uh, and then this is the output, okay? And that's the other input. Oh, okay. I see. Okay, so the squares are input pins. Okay, so that we have two input pins. The diagram is poorly drawn. So this is an input pin, this is an input pin, this is an output pin. So the propagational delay is measured as the time between the time when the input pins changes the state to the time that the output is correct. So there's a very slight delay in the circuitry in order to update the output. Yes. It's mostly because of the resistor, capacitor, the resistor, and the inductor effect. You cannot change the state of the transistor instantaneously because there is a resistor and an inductor slowing down the current, slowing down the flow of electrons in order to change the state of the capacitor. Yep. From the time the input pin. So let's say, let's just theoretically say that the input pin is here. So there's a time between the changes made to this input pin. to the time that this transistor is either turned on or turned off as a result of the change to the input pin. It is some kind of a lag. You can just call it a lag. Okay, but the technical term is a propagational delay. Not because of the same mechanism, but same idea. Yep. All right. So are we good with the concept of a propagational delay? Okay. All right. So now we go back to the previous diagram. And this time I'm going to look at the layers, and then we're going to turn off layer 2. And let me see. Oh, don't. I wasn't using the right layer. That's okay. Hmm. Let me see. What should I do here? Hmm. I kind of need the area. Okay, I know what to do. This is what I'll do. I'm going to start a spreadsheet on the side. But since I need the spreadsheet to be compact, I cannot use a browser. Well, actually, this is not much worse than a browser. Not much better than a browser. Okay, well, we can still do it like this. Okay, so here's a spreadsheet. And then what we'll do this time is we're going to take a look at the nodes. Okay, so let me describe what is a node in an electrical circuit. So a node in an electrical circuit means a copper wire, a conductor. Okay, so there's a node right here. Okay, this is a node that connects from the input pin to one of the inputs of N1. We'll call this node number 1. Okay, and node number 2, no, for no particular reason, is going to be this node here. So node 2 actually connects 3 things together, but it is just one single conductor. This is node 2. Does everybody understand the concept of a node? It is basically a single conductor of possibly very weird shape, but if any connection to that node changes, the rest of the node is going to get that change because they're electrically connected. Are we okay with that concept? So a node is not a wire. It can be a bunch of wires that are interconnected. Is that okay? All right. Okay. Very good. So that's node number 2. And then we have node number 3 here. Okay. So node number 3 is the one that I'm highlighting right now. Okay. So we'll call this node number 3. And then this one is going to be node number 4. So this is a relatively simple circuit with only 4 nodes. And then there are a few components. We have X, Y as input pins. We have Q and Q as output pins. And then we have N1 and N2 as NAND gates. Each NAND gate has 2 inputs and 1 output. Okay. So what we'll do is we're going to describe all the connection points. And then we'll label the connection points with the nodes so that we can understand which node is connecting which pin of which component to which pin of which other component. Okay, so here we go. So we have X, and X is an input pin. It only has one single um, port. Okay, it's the input port. Y is in pin, so it only has one single port. So basically, the term of a port is a connection point. Okay, every time in Logisim, you can start to draw a wire to connect to something. That's a port. When you hover your mouse pointer over a component and it turns into a circle, that's a port. Okay, a port is a connection point in Logisim. So that's XY, and then we have N1. So N1 is a little bit more complicated. It has 2 inputs, so in1, in0, and in1, and has one single output. N2 is kind of the same way. So I'm going to have to make the columns a little bit narrower at this point, okay? But N2 is kind of the same way. I can just copy these 3 cells over like so. And then finally we have Q, which is just an output. It only has a port, and then NQ is also an output which has a single port. So now we kind of shrink all of these also just to make it easier to read, like so. Are we okay with this table so far? Does everybody understand that X is a component, it has one single port, Y is a component, it has a single port, N1 has three ports. Two correspond to the input, one correspond to the output, and so on. So are we okay with the naming of the ports? All right. So you can see that I skipped row one because I'm using row one to indicate how the ports are connected. So we now take a look at X. X uses net or node 1 to connect to the first input of N1. So these two are labeled 1 because they both connect to node 1. Y, on the other hand, connects from with node 4 to the second input of N2. The second input of N1 connects to node 3, which is also connecting to N2's output as well as NQ, and then the rest are fours, excuse me, twos. So 2, 2, and 2 here. To make it a little bit more easier to read, I'm going to merge the columns. Oh, okay, it's under cells, and we want to merge. Nope, that's not how we do it. All right, so let's see. Merge. There we go. There we go. It just makes it a little bit easier. Visually, we can tell that these are basically the same component, like so. Okay. Are we okay with this table so far? I have just captured the design, in the graphics, on the graphical side, into something that is logical, into a table, basically. Are we good? All right. So we're going to start the analysis by saying, let's just assume that we don't know anything about this entire circuit. In other words, we'll put question marks over the entire thing. So question mark, and then we'll just copy the question mark. Oops, I pressed the wrong key. Okay, home, there we go. Control C, Control V, Control C, Control V, Control C, Control V, and paste one more time. Okay. So that's kind of the initial condition. Okay, so I'll just call this the initial condition. You're not told anything about the current state of the device. They're all unknown. Is that okay? So the first thing we want to do is like, okay, we'll just kind of replicate the experiment that we had a little bit earlier. We're going to change x and y from unknown to zeros. Okay, so we'll go here, turn this to a 0, and turn this to a 0. Okay, so I'm going to go to the comment here. This is what we call a node connectivity role. Okay, so NC stands for node connectivity. I will put it on here. It's node connectivity. In other words, based on how things are electrically connected, once I change x and y to zeros, which other ports should be changed to zero, basically, you know, really, really quickly. We'll call that simultaneously. Yep. That is correct, because it's all based on node connectivity. So that means anything that connects to node 1 should also see the 0 at cell A5. Okay, who else is on node 1? Aha, right here. This is N1's first input, so that should also see a 0 here. So I'm going to put a 0 there, okay? And these two I will boldface because these are changes from the input pins, which is not internal to the circuit. They are not changes from inside the circuit. They're changes initiated from something outside the circuit. Yes. Um, Yes. In fact, at this point, we don't need this picture anymore because all the information in the picture is already captured here. So for those of you who still want to look at the picture because you don't have it in your notes, I can do this. I think this is a pretty nifty trick. I know it is simple, but it is a lot of times it's the simple stuff that makes it kind of neat. So now we have a lot more area for the table, and then the picture is just on the side, and we can now bump up the font size. Is that good? Yep. All right. So node one, this is a zero, and also node four, okay, because this zero is presented to an input pin on node four. So the only other node four thing, or the only other port connected to node four is here. So that also turns into a zero. Do we have any questions about how cell C5 and cell G5 got updated to zeros? Okay, so this has to do with electrical connection. Okay, if you think about the circuit board, it has to do with how the copper on the circuit board is connecting between the components. Is that okay? So here comes the fun part, because we alternate between NC and PD. So PD is just an abbreviation of propagational delay. So that means after a propagational delay, what can we conclude about the output of our devices here? Or maybe sometimes maybe nothing has changed. Okay, so we want to know whether something is going to change or not. So the analysis of the PD row is to look at the immediate, okay, take it back, is to look at the NC row that is immediately above it. And then we look at the changes to the input pin of devices. Okay, so let's focus on the input pin of devices. Okay, uh, okay. So we take a look at this row here. Okay, so I just want to kind of help you guys focus on which part of the screen we're looking at here. So are any one of these zeros correspond to the input of a logic gate or some other device? Yes. Uh-huh. Yep, that is correct. Okay, so this zero corresponds to one of the input pins of N1. This zero corresponds to one of the input pins of N2. Now, the next question is, after a certain propagational delay, can we tell how N1 is going to change its output, or is it still unknown? Because remember, from the perspective of N1, the second input, which is in 1, is still unknown. Okay, we have only known one of the input pins to N1. The question is, only knowing one of the input pins of N1 is now a 0, can we tell what the output should be? Yes, and go ahead. Mm, well, okay, so the way we think about this is we have to remember N1 is a NAND gate. If at least one input is a 0, then the output is guaranteed a 1, regardless of what the other one is. What do you mean by the second connection? We don't. We do not, because just knowing one of the input is a 0 guarantees the output is a 1. And the same thing over here. It also guarantees the output of N2 being a 1 as well. Okay, so I will pause here because are there any questions about how I came to this conclusion? Yep. Can you name the cell, like the column or the row number? So you're referring to E6 and H6? Okay. So do you remember the truth table of the NAND gate? Okay, so how do we use the truth table of a NAND gate to come to this conclusion? Well, okay, so the first thing is to take a look at the NAND gate. Okay, so I'm gonna give put a little truth table over here. This is X, this is Y, and this is X NAND Y. Okay, the truth table has 4 rows. Okay, you should not need to copy this because this is actually discussed in the first week. If you do not remember this, or if you do not remember where you have seen this, you might need to study a little bit more. Okay. Now, when I say study, I don't mean to memorize. Okay. You need to at least know what stuff is where. Okay. Because the test, the exam is open book and open notes. Okay. Which means don't spend your time trying to memorize things. Okay. Spend your time to try to understand things. Because once you understand, then you naturally will also know, oh, okay, I get it. I know exactly how this truth table is created. Okay. So you look at this truth table, and then you look at my conclusion that if N1 has at least one input pin being a 0 being the first one here, the output is guaranteed to be a 1. How do I use the truth table to come to that conclusion? Yes, that is correct. Okay, in other words, if we look at this x here as in 0 and we look at this y as in 1, these two rows says no matter what y is, as long as x is a 0, the output is guaranteed a 1. That is how we make that conclusion. Yep. Propagational delay? Yes. hmm So after a very small delay, after the NC, after a very short delay, the output will change. Nanoseconds. Yep. hmm With the current transistors, we are probably looking at a fraction of nanosecond. Just because they're so small, the transitional time is very little. Okay, does that make sense? Because one row is only responsible to say, okay, electrically, because of these nodes are connected electrically, if this changes, who else is supposed to change also because of electrical connection? That's the NC. The PD, on the other hand, says, oh, okay, the input of some device is changed. The output of these devices may change as a result. So the PD row is responsible to reflect the change of the output of devices because at least one of the input pins of those devices has changed. Yep. Post what? It's not so much the current, it is the electrical potential. It is maintained. It is maintained. Correct. Yep. hmm Um, later I can give you a timing diagram. Sometimes it helps to kind of look at that. But for the time being, we're just going to say, okay, after a very short delay, the output of N1 becomes a 1, and then the output of N2 becomes a 1 from unknown, okay? Because everything started off as unknown. Are we good so far? All right. So now we alternate, which means the next row is going to be NC again, which basically says, oh, okay, great. N1, the output of N1 and N2 are both changed to from some unknown value to ones. So now we have to say, okay, but where are they connected to electrically? How are they connected? So now we look up the output of N1 first. It's connected to node 2. So that means the next NC will update everything else that connects to node 2 to also to a 1. So that means, okay, let's look up all the node 2. This is also node 2. Change that to a 1. This is also node 2. Change that to a 1. And we also have to look up everything that connects to node 3. So this is hooked up to node 3. It is also changed to a 1. This is also hooked up to node 3. It is also changed to a 1. Is that okay? Yes. Yes. Through the conductor, through the wiring. Yep. That's exactly what NC is doing. PD is within the device, depending on how the device is constructed. Within the device, there's a delay between the change to the input pin to when the output changes. Okay, so after an NC, we go back. Oh, I did something stupid. They're not supposed to be on this row. They're supposed to be on the next one. Okay, so node 2 is here, node 2 is here, node 3 is here, node 3 is also here. I do apologize that I put the update on the wrong row, but I think it's still being recorded, so yep, it is being recorded. All right, so other than my little snafu, is everything okay? Okay, all right. So after this NC, we need to go for another ND, a PD, sorry. So we need to go for another propagational delay because this one is corresponding to one of the input pins of N1. This one is also corresponding to one of the input pins of N2. So that means potentially something may change. So now we go to another PD row, and then we look up this thing here and go like, okay, is N1 going to change its output after a certain propagational delay? The answer is no, it's not going to change because in 0 of n1 is still a 0. So that means the output is still going to be a 1. And we don't write a 1 here. So we don't put a value in a cell unless it is an update from what it used to be. Is that okay? This is how we can tell whether there was an update or not. Okay, because if we update the entire table and just copy all the values, it just gets really, really confusing. So right now it's not confusing. Okay, so column E doesn't get an update because that one is maintained. And the same thing applies to column H. That one is also maintained because even though we just changed in 0 of n2 from unknown to a 1, guess what? In 1 is still a 0, so that means the output is still going to be a 1. It was a 1 already, it's not changed to a 1, so I don't put a value here. Whenever the PD row is empty, that means we are now at a steady state, which means there are no further updates. Okay, so I'm going to put a comment over here. This is now in steady state. And I will move the column a little bit just so that it's easier to read the conclusion that we are in a steady state. Are we good so far? All right. So we're gonna go change one of the two input pins from a 0 to a 1. You guys get to choose which one. But we're gonna change one, not both at the same time. Do you want to change X or do you want to change Y? Change Y? Okay, fine. There's something about Y. Okay, we'll change it. It's always the second one, the last one. All right, so we changed input pin Y from a 0 to a 1. So what this means is X is maintained. Okay, X is still a 0. That was not changed. So now we perform NC again. Okay, so we all start with NC whenever an input pin is changed. So now the question is, who else is connected to node 4? Uh, yeah, column G, okay, is also connected to node 4. So we put a 1 here. Does everybody understand why G9 is updated to a 1? Because of node connectivity. Okay, the electrical signal just travels through the copper wire and updates all those other pins connected to the same node. Okay, so the question is, do we need to worry about the PD now? The answer is yes, very good, because the previous NC row just changed the input of one of the devices. N2 has one of the input pins changed. The question is it changing the output as a result of that? The answer is also yes, because, okay, I don't think I need to explain that because the whole explanation is at the lower right hand corner, the truth table of the NAND gate. In the next row. So because that's the propagational delay. The propagational delay only wants to reflect the update to the output pins. The next NC is going to say, oh, okay, I see that the PD has changed one of the outputs. Which node is this output connected to? It's number 3. So who else is on number 3? Column D. So that one is changed to a 0 as well. And also, NQ, which is just an output pin. That's all, that's all it is. Okay. So after an NC, we always go for another PD. Okay, we always start with an NC and then we go to a PD. Depending on the output of the PD, we may have to go back to NC again. So now the question is, do I have anything to update on this PD row? And why not? Because after all, we did change in one of N1 from a 1 to a 0. That is correct. Well, yes, the output of N1 is still a 1 because instead of having just one of the two input pins being 0, now we have both of the input pins being 0. And the output is still going to be a 1 because of the truth table. And this is not a Elon Musk. This is a Vanna White. Many of you do not know what I'm talking about because you're way too young. All right, so that means we are now at a steady state again. So now we go for the last one, and this one is not going to be a choice from you guys because I want to replicate the experiment that we just did earlier, except I just explained everything very casually. Okay, so this is the third update. The first one is to change x to a 0 from unknown. The second one, oh, change both x and y to zeros from unknowns. The second change is to change y from a 0 to a 1. And this is the third one, which is to change x from a 0 to a 1. So once again, we start with an NC, and we have to say, okay, who else is on node 1? Okay, there's only one more thing on node 1, which is column C. So now the column C has to change to a 1. And because column C corresponds to one of the inputs of N1, now we have to go for another PD and say, okay, is anyone going to change as a result of this? The answer is no. Okay, we're done because the only device that can change because of this PD is N1. None of the input of N2 is changed as a result of the NC row that is immediately before this PD row. So that means I don't have to worry about N2 at all. I only have to worry about N1. But at this point, N1 has in 0 being a 1, but in 1 is still a 0, which means the output is still a 1. But it had been a 1 for a long time already, and it continues to be a 1 here. But we don't write anything that is not a change. So this entire PD row is once again empty, which means we are now at the steady state again. It came to exactly the same conclusion that we did a little bit earlier in the form of a truth table in a sequence. It's not exactly a truth table in the sequence of changes, but I did not explain it in a formal way like this. So are we okay with this table? There are a few things that we need to understand. One is why, okay? What does it do? This table helps us analyze how changes are propagated through a network of logic gates or other devices, okay? So that's the why. And also the what, okay, at the same time. And then the how is basically the format, okay? The format is it alternates between NC and PD. NC or node connectivity basically says one of the things is changed, okay, based on the conductivity of the copper wire. Who else is going to change? Okay, that's NC. But an NC row is always followed by a PD row. because in most of our designs, um, you know, as the result of an NC row, the PD row would basically look at the change of at least one device would have at least one of its input pins being changed because of the previous NC row. So the PD row analyzes those devices and asks the question, based on the state of all the inputs of the device known up to this point, are we going to change the output pins? Because there are devices with multiple output pins, a NAND gate only has one single output, but potentially there can be multiple output pins. So are we doing okay so far with this? Cool. All right. Let me take a look at the time. We only got about 10 more minutes. So I want you guys to analyze this. Okay, so this is going to be a fun exercise. I will not tell you what is going to happen. Okay, I'm going to duplicate the sheet here. This is the second one. So I am going to erase basically the rest of this so that you guys can kind of have your little exercise. The only change is I changed both input pins from zeros to ones. Yep. What? A strobe? Uh, yes. But why does that happen? Right? So I want you guys to perform the same analysis that we did earlier, but apply to this scenario, which doesn't seem too bad, right? I mean, we already had the cases of changing just x from a 0 to 1, and then the other scenario of just changing y from a 0 to 1. This doesn't seem too bad. We're just changing both x and y from zeros to ones. But it is no longer, there will be no steady state anymore. Okay, at this point, I don't need any further changes to the input pins, and it will never rest. Okay, there are probably terms, in electrical engineering for something like this, but you know, you can ask ChatGPT about the term that describes this particular scenario. It's an oscillation, okay? But I want you guys to go through the same exercise to find out exactly the mechanism of the oscillation. All right. So this is kind of like an informal, homework assignment. Um, I would say the informal homework assignments are probably just as important as the formal one, as the ones that are in the lab that actually count for points, because these are direct ways that you can work with something with your hands to help understand, first of all, what kind of a table it is, because I will talk about the solution on Thursday. Okay, so that means well, actually, I take it back. We'll talk about the solution next Tuesday because on Thursday we'll talk about exam one. Are we doing okay so far with this? All right. All right. So with that said, okay, when you guys are ready, I can kind of switch back to the slide because I do want to talk about floating point just a little bit more because that's going to be your lab today. Okay. I don't want you guys to be caught by surprise. So when you guys are ready, let me know because I can see some people are still copying. But I tell you, it's recording. It's being recorded. So you don't trust me, which is I cannot blame you. Yes. The top left. I think today is fine because I think certain days I forgot to change the resolution. So today I remember to change the resolution. So this is displayed by 1280 by 720, which is also the recording format. On the days when it recorded only a corner, that's because I forgot to change the resolution. All right. Are we good? Ready? Okay. All right. So I'm going to switch back to floating point numbers just for a moment because I want to see if you guys have any questions about floating point numbers. And really, I'm not kidding. I think you guys might think that I'm kidding, but I'm not. Um, the only thing you need to know is how to read this part of the formula because it describes exactly how to interpret the bits of a double precision floating point number. So do we have any questions about this part? And I will just kind of quickly go over the terms again because you will see those terms in today's lab. This is the sign, okay? It controls whether the rest, it controls whether, VD of F is positive or negative, okay? So this is the sign. This part here is the mantissa, okay? It is the mantissa because it is not just a coefficient, it is guaranteed to be at least one. I mean, do you think it is at least one? Do you see any chance that it is not at least one? It is one plus, okay? What are we adding to one? We're adding to one some kind of zero or one times some power of two. None of that is negative. So there's no way this whole thing can be less than one. But then we also know that this quantity here cannot be two, okay? It can get very close to two, but never two, because we're only adding the largest value that this can be is when I equals to negative 1. When I equals to negative 1, it is 2 to the power of negative 1, which is just a half, okay? And we are either deciding whether we have none of the half or we have one of the half. So that means the rest of the terms, if it's negative 52, we are adding potentially a very small number, which is a negative power of 2. So the bottom line is this part here is known as the mantissa. And then the last part here, okay, is this portion here. Now this portion can be confusing. This entire thing is the exponent, is the unbiased exponent of 2. In other words, it is the power of 2, but you have to remember it is with the subtraction of 1023. This entire thing is now the unbiased exponent of 2. Okay, if there's an unbiased exponent, you probably can guess that, yeah, there is a biased exponent. The biased exponent is just this part here in the parentheses. That is the biased portion of the exponent, which to you looks just like base conversion because that's exactly what it is. We are looking at the 11 bits for the exponent of 2, and we just say, okay, give me the unsigned interpretation of those 11 bits, which makes it range from 0 to 2047. It cannot go negative on its own. But if we are to subtract 1023 from a number that can go from 0 to 2047, then we have approximately half of them being negative and the other half being non-negative. Is that okay? Do we have any questions about the terms? And these are all in base 2. Okay, so the question that you will see tonight is asking you about the base 10 representation of a binary thing. Okay, I'll give you one more example, just so that you can get a little head start and not have questions about the format. Okay, so let's just say that the mantissa is this. Okay, this is the mantissa in base 2. So the question will ask you about the base 10 value of the base 2 representation. So in base 10, this is 1 plus a half plus an eighth plus a 16th, which is 6125, I think. Does it look right to you? I think that's about right. Okay. So after you add up all these things, you have 1.625 plus 0.6125. So the whole thing is 0.68625 in base 10. So this is what you need to enter as your answer when the mantissa in base 2 is that. And also, one more thing, unlike the previous test where you have infinite retries, this one only gives you 3 tries. So because I can only work out certain number of test cases, I don't want to kill myself making like a bazillion test cases. Yep. No. It will ask you about different components. That's just the mantissa. It will ask you about the unbiased exponent. It will ask you about the sign. It will ask you about the actual value being represented. But don't go yet. You need to know the passcode. Alrighty, give me a second. All right. So the access code is VD, which has nothing to do with the vice president. This has to do with the function name that I used. VD, yes. Yep, you have three, remember, three trials. Okay, so, just time your trials. Alrighty, I'll see you guys at the lab. Almost forgot to set it up. Alrighty.